Hello.
Hello. Welcome to another Papers We Love. We were maybe not very smart in having this be right before Memorial Day weekend.
We didn't realize. Yeah. Announcements.
Announcement. If you don't know, we are doing a conference, PWL Conf, in September 28th in St. Louis. It'll precede Strange Loop. Yes. Sorry, Strange Loop. So it'll be really fun. The lineup will be announced shortly, and if you want to sponsor, we will gladly take your money.
Yeah. Yes. We want money.
Was there anything else? Bathrooms are outside and to the left.
The lineup for the rest of the year is going to get published in a few weeks. So if you're still interested in doing a mini, let me know. We have a Slack channel. Like, if you have any questions, you can find us there. And
we're always looking for new spaces to host. I don't think we have a space for next month yet.
I don't know.
So if you have a cool space that doesn't have an NDA and has good AV, we would love to talk to you.
Okay, then let's get started. All right. So for those of you who are new, normally what we do is like a mini, and it's a shorter talk, and then we do a full-length talk. And I introduce speakers, and we make stuff up that may or may not be true. So Lukasz is an operation engineer at Wikia, where he is hard working on saying no. Between no and no, he focuses his work at modern approach to monitoring distributed storage. He also owns a small pineapple farm off the coast of Sweden. Let's give it up for Lukasz.
Hi, I'm Lukasz, and I will be talking today about fast inverse square root, which is a paper published in 2003 by Chris Lamont, if I'm correctly spelling that. And the paper is pretty old, but the entire history behind this paper is even older and quite interesting, in my opinion. So let's get started. So this is basically what we are talking about, and it's not really interesting. Like, it's just a math operation, right? The interesting part is starting when we realize where we are using this operation. So this operation is used very frequently whenever we are calculating normal vector for any surface where we want to calculate, I don't know, like lighting or any shadowings or anything like connected with like moving objects. And it's especially important, or it used to be especially important in games. And as you can imagine, like especially in first-person shooters games, you need to calculate those things like very, very fast, every second, every frame from multiple locations. So it's extremely important to calculate the entire operation as much efficient as possible. So this is the example of, calculating those vectors. We see multiple vectors that needs to be calculated at the same time just to make another operation slightly later. This is how it looks like when you actually, put some textures and you start playing games. So whenever you fire, there's like many objects that needs to be recalculated at the same time. So, but let's back to the paper. Does anyone know what that date is? Because it's pretty important date. No. But this is a extremely interesting and super important date for me, at least, because as an ex-gamer and ex-really heavy gamer, at least in high school, this is the date when source code of this game was released. Like, I'm pretty sure everyone at least recognized that game, or what game it is. And this game was released in 1999, December 1999, but in mid-August 2005, the source code was released. And the pretty interesting function was involved inside that source code. So the source code is available on the GitHub, so everyone can just go there and see exactly how it works. But this is the function. And this function is basically based on 4 steps. I'll explain those 4 steps just to better understand what is so interesting over here. There are pretty funny comments around. Those are original comments from authors. So let's go through that. So besides some simple assignment of variables, this is the first main step that is done over here. And in this step, the floating number is casted into integer just to make some operations in the next step, which is a clever trick because at least in early 2000, it was extremely difficult or extremely heavy to calculate floating numbers. It was just easier to do integers. So in the next step, if we forget for a second about this weird constant at the beginning, we will get back to that later. What we are doing is the integer from the previous line, we are just shifting right by bit shifting right by 1 bit, which is basically dividing, which was a cool trick back then. It's still used right now for some optimizations. And it's basically dividing by 2. We're removing last bit, and suddenly we got a half of the previous number. And the result is there's also this constant number that we'll get back to that later. So in a third step, we're basically doing what we did in the first step. We just revert the casting back to floating number just to get back to what was originally. The only difference is that it's just modifying number with the previous line equation. And then there is the last step, which is a Newton method of improving the approximation. And as a result of this line, we are getting very, very good approximation of inverse square root, which is like 4 lines. Not really a lot is happening over here. There are 2 basically just conversion from float to int, from int to flow, and 2 weird lines. So author of this paper is going really deep what is happening in those 2 lines. So I thought it would be interesting to at least present what is happening in this line. We will get back to step number 2 later, because first let's try to understand what's happening in step 4. There is a lot of math to prove what is happening with Newton method of approximation. But the important thing is the method allows us to guess with couple of approximations what's the root of any function. We just put the function, we are starting guessing, we are solving the equation, and with every iteration we are getting better and better and better and more accurate with our result. It is like, I'm not going through all that math because it's just boring. I will show you what is happening over here with a quick example. So let's assume we want to calculate 1 square root from number 2. We took number 2, then in the second line you see the proper result, that's the correct result. And we are starting guessing with, let's say, we think it's 1. So let's start with the equation from previous slide. We put 1, we calculate, the result is 0.5, and we know that this result is correct in like 70%. So it was okay, but not really great. So let's take the result of this equation, and let's put that result as our new guess. So in a second iteration, we put 0.5 as our guess, and we start again calculating that. We see that result is 88% of what we should expect. And then, of course, we can make more and more iterations, as we can see with 50 iteration, we got almost like 99 and a couple of nines after correctness, which is like really, really great. So if we get back to our source code, we see that this is exactly the equation that we are solving over here. The only difference is we are doing that only one time, and that's it. So based on the previous slide, you can start thinking like, yeah, so it's highly important to start with a good guess. If you start with a good guess, your result will be instantly extremely accurate. But how to guess correctly, what's the first guess is. So now let's move back to our second step, because in our second step, we basically calculate our guess. And this is the weird constant that we are using over there. And from where is this constant? This constant is called, people call that a magic number. A magic number that is not really that magic, but allows us to get result with correctness below 0.1%. So it's like super accurate. If we put that in equation, we solve the equation, we will get the result extremely accurate. So the next question is like, how do you even end up with this constant? Like how they guess that number? The author of this paper is suggesting at least two authors of this number, but I did a little bit more of investigation what is happening over here. So there are a couple of forums where you can read about that, but at one of these forums, people started asking, like, basically they start with John Carmack, who's the author of Quake-Free Arena, like, hey, how did you end up with that number? And he was like, no, I don't know. Maybe it was a Terry. Who knows? So they did more investigation. They asked Terry. Terry said like, nah, it's not me. I was using that because it was around. So maybe it was a Gary. Gary used to work in 3dfx, but before that, he was working in Iris. And he was one of the guys who built that box. And that's already early 90s, like mid-1991. And he also answered the email, and he says like, it looks like my code, but I'm not exactly sure like who really invented that. It was, I don't know, it was so many years ago, so I don't know. And basically, after that answer, the entire investigation just went cold. They assumed that it was somewhere around working on this box, and that's it. But a couple of years later, someone suggests that the author might be completely different. It might be way earlier than 1991. If we go to this link, there is a standard free distributed CMAF library that it was used in Sun Solaris, at least developed by Sun Microsystems. And in this specific file, there is a huge section of comments. I'm not sure if anyone over here ever read the source code of Sun Solaris, but I was pretty impressed. There's like 100 lines of code and over 400 lines of comments. So, but one of the section is starting with this information that this is a draft paper from Professor William Kahan from 1986, and just below that we see pretty similar equation that we are using earlier in a game. Of course, the constant is a little bit different. It's less accurate. It's not that great as it used to be in 1999, But apparently over 10 years, people were just using this equation and just improving and improving the variable just to get as best a result as possible. The author of this paper also calculate and prove in a mathematical way that it is possible to get even better result with slightly different number. It's more or less the same, it's just a little bit different. And it's possible to calculate that for 32 bits, 64 bits, and basically any other system that we can guess, like 128 or so. So we know it's super old. It was created by a person who is the author of standard of floating points. The Professor William Kamm is a person who standardized double floating points. But I was extremely interested, like, because we got 2017 right now. It's May 2017. If this trick is so cool, why there is only like 20,000 pages in Google about this number? Like, there should be like basically everywhere. Like, it should be like basically the standard of any calculation of that. So I decided to check how it works. So I basically copy-paste the code from Quake and just run that a billion times. I know people can count like cycles, like I'm not that good with C, but simple loop, billion times, let's see what will be the time. And just to compare that, I use the standard function available, and just do the same thing again. And that was the result with the modern hardware. Suddenly, this hack is 2 times slower than what we get right now. And in a paper, authors suggest that it was 4 times faster in 2003. And when the game was released, it was even more faster. So what happened between 2000 or 1999 and 2017? So I started reading more about this topic, and many people were. I discovered there are some forums, Intel forums, where people are basically running this kind of test where they're calculating cycles over and over with every single CPU, with every single version of CPU, and they're just trying to catch if there is like any performance degradation, any improvement. Also, just before the Quake was released, Intel, for the first time, released a CPU with extended instructions, where they started challenging that problem. And over time, those external extended instructions started allow people to calculate this kind of operations and many others in just efficient way. So suddenly it's just faster. Yeah. Standard Ubuntu GCC from the latest stable version. I did not really investigate that part so much. I was just impressed that it's suddenly just slower. I did that on a couple of machines, so there was like different compilers, and everywhere it was slower. So that's basically it about this paper. The trick is really cool. Some things are still, I would say, important. If you want to do some optimizations, like those beat movements, like still around, people still are using that. But the magic number is not that magic, and actually it's just slower right now. It's not really important to use that thing anymore. And that's basically it. Thank you.
Questions? Okay.
So I designed a square root algorithm for the Itanium. For the Itanium. And when you did the 1 over square root, it's actually worse than you think, because the way they calculate it is they first approximate to get the 1 over square root, and then they divide it. Then they divide it into 1. So there's actually often an inverse square root function available to avoid that final division, and then it would be even a bigger difference.
Okay, that's interesting.
Did you know XKCD mentioned this?
Excuse me?
XKCD mentioned it.
Yeah. Oh, yeah.
Yeah.
I know what's the more accurate version, right?
It talked about that, but it was more or less just saying for every gem like this, it's hidden away in source code somewhere.
Yeah.
Yeah. Right. Thank you.
What is the numeric value of the magic number?
Oh, it's like 15 million something. It's like just a integer. Yes, so the author of this paper actually did that. He basically calculated what's the most accurate one. This one is really accurate. He was able to do one that is like 200 lower or higher, and it was slightly better with a second approximation, because it's also important how many approximations you will do. How accurate it's after first approximation, how it's accurate after second approximation. That was two cases that he was comparing. And he was able to get like a slightly better result, but we are talking about results with a precision below 0.1%. So it's really accurate.
Is there a range of numbers in which this approximation works well, or is it for all integers?
So that's the funny part. It works for everything. That's why it's so magic. I mean, as long as you are in the same range, it's like 32 bits or 64 bits. There are different numbers for different types. Oh, possible.
Okay. All right. Thank you so much. All right. So everybody, this is Ben. Ben is the co-founder and CEO of Lightstep, a performance management solution that ties complex distributed systems performance to business goal and objectives. An expert in distributed tracing, Ben is a co-author of the Open Tracing Standard, a Linux Foundation project under the Cloud Native Computing Foundation. Previously, he built Dapper, Google's production distributed system tracing infrastructure, and Monarch, Google's fleet-wide time series collection, storage, analysis, and alerting system. Ben holds a bachelor's in mathematics and computer science from Brown University, and in his spare time, Ben moonlights as a cardio bar instructor. Let's give it up.
Thank you. That bio was not the one that I wrote. That must have been through marketing. My bio says I steal snacks from Google, not that I ever accomplished anything in my career. So speaking of not accomplishing things in my career, this is like the paper that love has many forms. This is like a jealous, like envious sort of love. Like this is the paper that I wish I had thought of writing myself. It's so good. And I'm actually friends with Jonathan who wrote this, and I just think it's like an awesome paper. Unlike most of the papers here, this is pretty recent. It was published a couple of years ago and won Best Paper at SOSP when it was presented in 2015. And so I was going to write up my own slides to try and summarize it, as you do if you're honorable. And then I asked Jonathan, hey, Jonathan, can you just send me your deck from this thing so I can just, take some diagrams or whatever. And anyway, this is like my usual presentations are pretty minimalist, like some stupid memes and like a lot of dumb talking. But this is this maximalist presentation. This is like PowerPoint hacking, what you're going to see here. I ended up changing almost nothing because it's such a work of art. But it's kind of like, this is like karaoke presentation here. It's just so intense what's going to happen that all I can do is just try and follow along. But it'll be fun. It's a really good PowerPoint deck, like the best PowerPoint deck I've ever seen in terms of just how much stuff is happening. Anyway, okay, so pivot tracing. He has a nice .io thing where you can check out some stuff about it. I really do think it's a pretty impressive piece of work, obviously, or I wouldn't have picked it. And, I'm kind of kidding about the envious love, but I do think it's really an incredible accomplishment, what he did. There's a baseline that's helpful to understand if you're going to understand pivot tracing in context. The first thing I would point out would be dtrace, which is a well-known paper and also a well-known system that Sun released that does dynamic instrumentation of we were talking about it before eating pizza, and it does really incredible dynamic stream processing, but on a per host per VM basis, and so that's sort of the limitation of dtrace. Then there's xtrace, which is a different type of tracing. Xtrace was one of the first academic papers to really go into distributed tracing in detail. It's not the first, but one of the first, and probably the closest ancestor of pivot tracing in terms of their data model. And then there's a system called Fay, which allowed you to write queries that ran over to the distributed system, which is what pivot tracing is going to demonstrate as well. Fay differs in that the implementation ultimately is such that it's not performant enough to run in a production environment, which is disqualifying in my totally engineering-oriented mindset, where I'm incapable of appreciating systems papers unless they're practical, which is a flaw, but it's a flaw that I have. Speaking of that flaw, it is related to Dapper, which I can't take credit for any of the actual smart part of Dapper. I did do a lot of work in productionizing that when I was at Google, and we did write a paper about it, which was rejected by 2 of 2 conferences we submitted it to. And the reason it was rejected is good, which is that it has no scientific merit at all. There's no hypothesis. There's no experiment. It's just it's basically just like a design doc. And then someone needed to cite it at Google, so he put it on the internet, and then people thought it was interesting, but it's actually not a scientific paper at all. There's nothing scientifically valuable in that entire piece of work, but it is relevant in that a lot of production tracing systems derive from that system, which again, I wish I get more credit for that than I deserve. The people who really thought it up were Mike Burrows and Louise Barroso and Sharon Pearl. And I just help them get it into production. So this is the now we're starting Jonathan's deck. This is the least flashy slide in the whole deck, but now we're going to get moving. All right, animations begin. So pivot tracing is about dynamically instrumenting live systems, which is something that in my mind is a bit of a holy grail, not something that has been practical. It also allows you to correlate in group events in a SQL-ish way, again, across a live running distributed system. And they decided to do their experiments on top of the Hadoop stack, which is fine. So let's talk about Hadoop stack. So there are disks. This is the minimum you need to know to understand the presentation here, right? There are disks. HDFS is just like a distributed file system that reads and writes from those disks. Above HDFS is HBase, which is like Cassandra, Bigtable, like one of these distributed hash table type things. And then MapReduce, everyone knows what that is, and MapReduce reads from HBase and writes to HBase, reads directly from HDFS and writes to HDFS. And then it also manages disks locally as swap files for various operations and optimizations. So that's the basic idea, and this is all running on a bunch of machines, of course, or VMs. Now, these blue overlays, this is my commentary, reminder to myself. I thought it'd be helpful in these sorts of presentations, especially given the density of the slides, to be these are the things that kind of made me think twice about what or get excited or something. In this case, it was just that normally request tracing in production is used for latency-sensitive workloads, and here we are starting with this totally throughput-oriented batch processing thing. And so immediately I'm well, why? What's that have to do with request tracing in practice? And we'll get to it. I think what's so exciting about pivot tracing is that it's not just for finding slow queries, which is what people had thought about tracing, as typically how people are thinking of tracing, at least in an industrial environment. Okay, so here is an example of a client reading directly through HDFS, and here's an example of a client reading and writing through HBase and HDFS down to disk. And here's an example of one of these MapReduce benchmarks, MR sort 100G and MR sort 10G, which, I won't read the diagram for you. You see what I'm saying, though? This is impressive work, right? Just keeps on going back and forth. I tried to import this into Google Slides. It was just like totally destroyed. So the question is, how is the disk bandwidth being used? Now, the naive thing to do here would be to use HDFS, has this thing called data node metrics, which is just like an interceptor layer where you can read out statistics about reads and writes and make a time series out of them. And you can do that pretty easily with any metric system that you want, Prometheus, whatever, it doesn't matter, graphite, to generate this sort of plot. So this should be familiar to everyone if you work in this industry, but this is just showing per host throughput megabytes per second. It's a trivial thing that you can get out of these metrics at the HDFS layer. Okay, great. But unfortunately, that's not really what you want, especially if you're trying to understand where that usage is really coming from. You just know what machine it's on, and that doesn't tell you where it came from. So what if you wanted to attribute the disk consumption to the HDFS layer instead of to the disk layer? So pivot tracing, to kind of motivate this, allows you have the same total amounts, but instead of breaking it down by which machine you're on, you're able to say, well, that came from the MapReduce job or from HBase, or directly from the file system read 64 4 meg benchmarks. Does this make sense? So now what we're doing is we're tracking a cost metric at the disk layer, or at least at the HDFS layer, via where this came from in a distributed system. And that's a very powerful thing. This is done without any code modifications. But we can even go higher than that, and we can say, let's actually go all the way up the stack and say you want to understand where things come from at the application layer, like above even HBase and MapReduce and so on, and that of course is also possible, and you can read all of that out as well. The original question was actually that Jonathan was trying to answer was about the disk, not about HDFS. So there in Java, you can intercept I/O stream stuff going to disk and do the same sort of tricks there. So you can even go one step further, and this would have been missed in the HDFS interceptor, but with pivot tracing, you can intercept at the I/O streams layer and get the final numbers where you can see both all this other stuff we saw earlier as well as direct disk reads and writes. Now, I'm going to sort of pause and I want to see if people are totally lost, because if you are, it's going to be harder to understand what's about to happen. Okay. It could mean lots of things. Yes? That's a very good question. To repeat the question, is this involve code modifications to get here? Kind of, and that's later, but not. But what's really important is the code modifications are totally local and have nothing to do with passing any particular information down the stack. It's and that's what the paper gets at. Jonathan is trying to do here, I think, wisely, is to illustrate the kind of result we're trying to achieve, and then this is used as a motivating example for most of what comes in the rest of this presentation. So that will come out. So this is hard for a couple of reasons. Wait, what's happening? God damn it. This is my comment. So, this is, in my mind, this is pretty awesome. I do want to say, and I don't think Jonathan did this in his talk, but in my mind, it's cool that you can build this dashboard. What's really, really cool about this is that you can build a real-time control system using this information. And if this is some multi-tenant thing, which it probably is if you're a big organization, you can use this sort of technique to limit the amount of disk reads and writes that these things up at the top of your stack can do. And Google does this with their Census project right now. So, they have one giant multi-tenant storage system for all their applications, and they can do read and write throttling based on, tokens that are sent down the stack. But pivot tracing does it in a way that's much more general and much more elegant, I think. Well, let me continue. I'm already way behind, and I think some of that will come out. But the value goes beyond dashboards. I think the presentation could have underlined that more. These are things that have been hard. Instrumentation historically has been decided at development time, and they aim to address that with this. Yeah, this is funny. He was illustrating that this graph that we saw here, there's an HDFS JIRA issue about adding that support to HDFS. And at the time of this paper writing in 2015, it hadn't been done. And with pivot tracing, it's just sitting there, and it's sitting there, ready to be used. I actually went back and looked up this thing earlier today, and it's still an open issue in HDFS, like 2 years later. Sad, but Jonathan's point is that you shouldn't need to know at the bottom of the storage stack what you might want to aggregate by at the top of the stack. And he also says dynamic dependencies are a huge problem for this type of analysis. And if you have a distributed system, especially with microservices where each thing is kind of stateless and doesn't know about the rest of the system, this becomes even more of a pernicious problem than in Jonathan's examples with a relatively small system. So let's move on. This is actually a graph that Netflix got out of AppDynamics, a super readable graph of their internal dependencies and all the communication between them. It's a bit infamous. It's actually generated by this guy Bruce Wong, who was at Netflix and is now at Twilio, and I think has come to emblemize like why you really can't be doing an analysis of your system with like the sorts of techniques that made sense when you only had 10 services or something like that. And that's what Jonathan's getting at here. So pivot tracing, you don't know the questions in advance, and you have to correlate information from different points. Okay, great. So let's get to the fun part. So they model everything as tuples. All the events in the system are tuples, and I'll get to that. And by that I mean just key value pairs, basically. And then they can dynamically evaluate relational queries over this data set of production stuff. Yes? Oh, cool. And then they introduced this new idea called a happen before join, which is super, super awesome, and I'll get to that. Let's get started. So what's happening here is that there's this data node metrics layer that has, it's like an interceptor, and there's this increment bytes thing. What you want to do with pivot tracing is extract a tuple from that says the data node metrics thing is called, the delta value is 10, and then there's a bunch of stuff you can extract from the local machine, like the host name and so on and so forth. You want to be able to get a tuple like that out of the system. And then when you're doing your analysis, you want to make a SQL-like query, and they wrote this little like miniature SQL language where you can say from this increment function in the bytes read function, I want to group by the host, and I want to sum by this delta. That gives you the thing that we started with in the very beginning. This is the thing that's easy to get out of the system without any kind of fancy tracing. This is all like totally local using that tuple. And what we call this thing right here is a trace point. And so every trace point, which is a concept that's borrowed from dtrace, every trace point encodes a place within an application from which you can both extract information and like interpose with the magic pivot tracing logic that does all this sampling and aggregation, so on and so forth, which I'll talk about later. But the trace points you can think of as this like kind of constellation of places within your code base where you can interpose and do stuff. And this kind of gets to your question. Anytime there's a trace point, you have a lot of flexibility. If there is no trace point, or you have no access to a trace point, then there's a problem. He uses the JVM Java agent stuff a lot, which does give you flexibility at any function call to add stuff like this. That wouldn't work in other languages, but so be it. So there are also like client protocols, which is another place that they interpose. And what you want to be able to do is correlate events that happen at one place in your stack with potential aggregates that are at another place in your stack. And the happen before join allows you to do that in a very elegant way. So you write these really compact queries, and you get these really powerful semantic things dynamically over your system. Okay, so let's suppose that a request first passes through these client protocols, and it produces a tuple in the client protocol that says name is client protocols, the procedure name is hget, and then we read off a bunch of stats about that, and then the request goes down to HDFS, hits this other trace point data node metrics, which we saw earlier. Okay, so that's great. So these invocations have the happen before relationship, and that client protocols happen before data node metrics, and pivot tracing keeps track of this in using this thing called baggage, which we'll introduce shortly, that allows you to that allows the system to understand that, oh, this is this thing I've been waiting for. I'm going to do some magic stuff, and I'll get into that in a minute. And then you end up with this join that takes place in here, where magically, and I'll get to the magic later, pivot tracing in this process, like in the runtime layer, actually has access magically to information from other parts of the stack, and that's propagated along with the request in a way that's totally dynamic and beautiful and amazing and everything. So the cool thing about this is we're trying to do this aggregation by something at the client, and pivot tracing with no intervention from the programmer is able to extract the fields it needs higher up in the stack and have them travel along until we're lower in the stack to satisfy this join. And once we've done the join, then it's actually a pretty simple aggregation, and we do it. So here we go. The full query is we're going to read this increment field. We're going to join it in this happens before join back to the client, and we're going to group by the proc name, and we're going to do a kind of classic, select sum aggregate in a SQL-like language. Do people understand what this is doing? Yes? Well, sort of, but that he gets into that too. But you have to. I'll talk about that in a bit. It makes sense? Okay. So this is like the crucial theoretical concept in the paper. There's a crucial practical concept as well, but the happen before join is like the cool thing from a theoretical standpoint. And then get your mind out of the gutter. That is a wrench. Okay, it was confusing to me. Unfortunately, it shows up a lot in this thing. Whatever. So that is a piece of luggage. I think that was easier. Okay, so anyway, so the implementation has this dynamic instrumentation thing. I'll be honest, as with any love relationship, I have some push-pull, and this is an area where I push on the paper. I think this is total nonsense, but that's okay. The rest of it's so great, and this is not crucial to the concepts here. But in pivot tracing, they present a dynamic instrumentation approach, which I'll get to, and then use this thing called baggage. So baggage, this is the crucial implementation concept, and we're about to talk about it. So this is super cool, in my mind anyway. It's sort of like a key value map, like in a hash table or something like that, except it follows around your system. More amazing imagery and animations. I have no idea how you do that in PowerPoint. But so this baggage it's like a key value map that automatically follows the flow of your transactions. And there is, so to the question about whether you have to propagate a UUID around, you do need to specify, or something needs to specify how the context flows to the application. But the context is not a UUID. It's actually this baggage map, which has a special arithmetic on it, which I'll get to in a moment. And it's kind of a generalization of metadata like a trace ID or something like that, and is a really powerful concept. And each transaction, even if it forks and joins and stuff, only has one set of baggage. So let's say there's two trace points. What you can do here is the baggage can arrive at trace point A, and we'll get into the full kind of algebra for baggage, but you can pack an element into it. In this case, because of the query, we pack the client name fsread. That baggage then moves on to B, where pivot tracing knows to unpack the client name, which it does, and it's then able to do what it needs to do with that baggage. And this is all facilitated automatically via this kind of like mini compiler they have. So here you can imagine lots of requests going and these dynamically instrumented processes that track baggage independently. So let's talk about how queries are actually implemented. you've got a bunch of workloads going through your system. The trace points, which are places where pivot tracing can add the instrumentation, are distributed thusly. And so what I'm trying to, this is the point I have to remember exactly what the point of this slide was, right? So you can export these tuples either from like the function definition or from the host and things like that. The things you export you don't pay any cost exporting them unless a query is installed. So later on, when they talk about overhead, the overhead of having pivot tracing just like in your system is basically negligible. It's only expensive if you decide to ask for tons of trace points doing tons of stuff, which is really important for the production system. So you don't pay the cost of everything you have access to in one of these trace points. You only pay the cost of things that you actually use. And with good queries, what you're using is pretty small. The query language, which we've sort of seen a bunch of already, is basically this idea that you have tables that you're choosing from. You can join in this happens before way across process boundaries, and then do a variety of statistics. And the output from all this is just a stream of tuples. So to me, it's incredibly exciting that this join, like the A and B, could be in completely different systems in your distributed architecture. Like you could have 500 microservices and those can refer to completely different things. And to me, that's just like an incredibly powerful thing that you can just write this query and just run that on your system. And in a way that's not performance, the performance degradation it can be negligible for reasonable queries. So pivot tracing front end has a thing called advice. So this is the other part of this that's really fun and cool, and this is the part that I would get super excited about if I was trying to implement this. You can write this query, and then pivot tracing needs to distribute information to all these agents. And what it needs to tell them, it can't know without solving the halting problem or something, which agent is going to be the one that actually does the crucial unpacking or the packing. So it's able to compile these sorts of little miniature programs down into advice that's sent out through the distributed system and says, well, if you find yourself doing this proc name thing in the client, you should pack proc name into the baggage. And if you find yourself observing this delta, you should unpack the proc name and you should emit this statistic. And you can do some batching and smart things like that, so it's not super expensive. The instruction set that they support is pretty limited for baggage, and it's very carefully construed such that everything ends up being locally reasonably efficient, and that you can get global aggregates out of these local aggregates. I think one thing that he doesn't mention is that for this to actually work, as far as I can tell, what emits needs to be commutative and associative. If, for instance, if what you were trying to do is compute the 99th percentile or something like that of all of these deltas, you'd run into trouble if you were computing that locally, because you can't take a statistic of a 99th percentile. So what you'd actually have to do is emit some kind of histogram distribution or some approximation and then take the 90th percentile later. What question? So there's a worked example of this in just a moment, and if it's still unclear, then I'll go into it. So what happens here, more amazing animations, is this thing that they call code weaving, and so the pivot tracing dynamically enables this advice at the trace points, and when you're evaluating in A1, you observe proc name, you pack it into the baggage, and then in B1 you observe delta, you unpack the proc name, and you send it off to the agent where it does something, and the does something is smart. It knows that we're computing the sum here, so it can buffer these things up, and if it flushes out every couple of seconds, it doesn't need to flush everyone over the network back to the central system. So it can do some local aggregation of these to save on the number of cross-process things. Yes. Yeah, exactly, yes. That's my understanding, yeah. I think I think since the device is kind of small per installed query, I think that's reasonable. It's probably order of like hundreds of these or something, Other midstream questions? Yeah, and the baggage explicitly follows the execution path, and it's evaluated inline during the request. So no global aggregation is needed to compute these things, and then you can centralize everything and finish your commutative associative operations. So every second you report the stuff back to the user, and if you're trying to, do one of these complicated queries, I would imagine, as someone who didn't write this paper, that to make this useful, you'd probably want to bucket things into like time quanta or something like that. And the paper doesn't go into that sort of stuff, but that is sort of an exercise to the reader or whatever. I mean, it doesn't seem like super hard. I also want to mention that Jonathan has gone on to work on this thing called the tracing plane, which takes this direction even further, and it makes the baggage operations that were here get expanded a bit, and it really decouples the idea of propagating context from the distributed system and having this baggage, which you can do some pretty complicated things with. I'm not sure how practical this is, but you can. So all these code paths we're talking about are pretty simple. A1 just calls B1. What if A1 forked and actually created like 5 parallel requests, and then you joined at the other side and did some batching? So what if you're trying to compute some sort of sum through that? Well, that's kind of challenging because the sums, when you join back, all need to be joined back together. And then the work he's done in the tracing plane is able to handle all of those cases quite elegantly, and you end up at the end with like the correct number. This stuff here, as it's written, you could construct some cases with forks and joins where it wouldn't be so clean. Evaluation. I'm going to kind of speed through this part because I just don't think it's as important. But it's done with a Java agent, and I just want to cover a few things I thought were worth talking about in particular. So I think this is total BS. This is, I'll tell you why. Okay, so first of all, I think it's just not true. This 50 to 200 lines of code per system, no way, man. I think the problem is that these things are actually relatively like well-factored code bases. Like these are significant, large open source projects. If you're dealing with application code that's like industrial application code that has a lot of like kind of cruft and legacy stuff in it, there's just no way that this is right. He's also in Java, which gives you some really nice affordances, and a lot of common use of core primitives like this and agents and so on, which allow you to interpose and do magic. I think that's not going to work in certain other languages where things are much more of a, there's like in C++ or something like this. This is just like total non-starter. In Go, like there are some advantages with the Go context stuff, but you'd run into a lot of trouble around dynamic instrumentation because you can't. So I think this is just not legitimate, but that's okay. Because regardless of how you end up getting this instrumentation in, one time, regardless of how you get it in, it is like what you get at the other side is super powerful. And I think that there are things of tracing, et cetera, that try to address this problem in the real world. But I do think the instrumentation overhead is pretty significant, and this dynamic approach he took works for certain types of systems. And Jonathan is a big proponent of aspect-oriented programming for this sort of instrumentation. I'm like a little iffy on that, again, for like really sort of complex, messy legacy code bases. I just don't think it's going to get you good coverage. But the overheads for baseline is small. I actually don't remember exactly how he took that benchmark. This CPU overhead here is, I think, pretty substantial. I wouldn't want to slow my system down by 15%. I also have a feeling that this is hindered in some ways by that dynamic instrumentation approach. If you did static instrumentation, the amount of work that's happening here is actually pretty small. And so I think that to a certain extent is another reason why that dynamic approach is a little questionable from from a code standpoint. And this baggage thing is super important because what we're doing here is every RPC between systems or any message pass between systems needs to add this number of bytes. And if you're trying to send like little 5-byte things around, you just multiplied your message size by 30 or something. So this is a potential problem. However, I think for systems like HDFS and so on, this is an acceptable overhead for what you'd be getting at the other side. Go ahead. He said with the queries from the paper installed. So the queries that the paper referenced generate that. And this, in fact, is why I think in production systems, this sort of stuff has been hard to sell because of concerns around either you truncate the baggage, which breaks it, or you don't, and you have this like unbounded thing you're adding to every RPC in your system. So that's probably the area. I know that Uber is embarking on something like this internally, and that's been like a huge concern. Like they want to add like security stuff using a baggage-like mechanism, which open tracing actually supports, and this is the area that there's been a lot of pushback about. So they need like white lists of which fields are allowed and specific things about how big they can be and so on. There's a bunch of experiments. I think I should do a time check. When do you want me to stop talking? Like maybe like 2 a.m.? Okay, 3 a.m. No, I'll try to burn through some of this stuff. This is basically what we saw earlier, and I do want to show one thing that was pretty awesome. So Jonathan found a pretty serious bug in HDFS through this work, and he thought it was like a bug with pivot tracing, but he was getting like a bunch of really weird performance from the replicated block storage. So HDFS is, this is probably well known, but it just for review, it's something where you need to have multiple copies of every piece of data, so you have multiple replicas and blah, 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 blah. So you have all these data nodes, and any piece of data will be on many of them at once, and there's an attempt, of course there's an animation, I don't know why I even talk, but the file is split into pieces, and there's this name node that knows, well, this file is on data node 2, 3, and 5. So if you want to get it, you can read from any of those. And by the way, you should use the one that's closest. So that's where the bug comes in. So the client says, let's get the block locations. Yet again, I'm trying to describe something. I know there's an animation. You get back this thing, and the policy is first, you try to read from the same machine. If you can't, you read from the same rack. If you can't, then just whatever, DRAND style selection, and so you read from the one that's close, and you get the thing back, and you're done. Okay, great. So now we have 8 worker hosts, and you have a workload generator that tries to randomly read from a large data set. So you expect to see uniform use of these hosts because you're doing this totally randomized thing. And so he wrote this test case because he was getting weird behavior. Fine. So you have this name node, and he expected uniform throughput. That's not what he got. Some of these hosts were consistently getting lower throughput, and he thought, oh, there's some bug somewhere in my code. Kind of looked into it, and then he decided to use pivot tracing to figure this out. Huge variations in throughput. This is a really bad thing because you have to provision these things for this black line, and you're not even able to touch it with these lower ones, and so you're wasting money or having bad performance or both. Is that hand drawn? Oh, okay, good. So his hypothesis is that there's a problem with the random lookup. So he writes a pivot tracing thing. Let's run it on our system, and what you get back is the number of times that you access these different block locations. And it turns out that when you actually do a group by across all of this data by the file name and the host, it doesn't really look that non-uniform and doesn't anywhere near approximate like how bad this looks. So okay, that wasn't the bug. Okay, let's try again. So maybe it's because some data nodes store more files than others. So you can actually do a query in pivot tracing for that, and what you end up with is something where it's like, well, actually they're all kind of about the same. And so Clients are selecting files uniformly at random, so that's good. And the files are distributed across the data nodes uniformly at random, so that's good too. Still doesn't understand what's going on. So maybe the choice of replica isn't random. So we go back and say, okay, it should be the same machine. If not that, then you read from the rack. If not that, you select randomly. And so he writes a query for that. And again, this is the sort of thing, there's no way that you could expect someone to have passed this data down in the stack, but he could just dynamically instrument his system to get this information. And what he ended up finding, so many slides. I'm going to get through this quickly. So he built this matrix using this group by query that he's written down here. And when both A and C host replicas, try and choose A 100% of the time and C 0% of the time. And when B and D both host a replica, the clients choose B 0% and D 100% of the time. And he goes through and builds out this thing. And it turns out that he was able to build this matrix very easily using pivot tracing, which ultimately revealed the fact that there was a place where clients were supposed to, a part of the system was supposed to be randomizing something that was actually just choosing the first item in the list, and so the sorting was totally static. And this is a monstrously hard thing to find out, that he was able to, reveal something that definitely did not look at all random with a couple of queries in his system. And this was like a bug that had previously been reported and no one could figure out what's going on. And this is like a really nice, easy way to demonstrate something really bad is happening that's reproducible. So that's pretty awesome, I thought anyway. So yeah, pivot tracing, this Happenworth thing is awesome. This wrench is awesome, and I wouldn't have chosen that. And then the causal tracing is also really cool. And he thinks those overheads are acceptable. I don't, but you could make it a lot faster, and it would be. So that's pretty much it. Any questions or anything? Okay, good. Thank you so much for listening. If you want to talk about the stuff, I'd love to.